Okay, I guess we can start our afternoon session. I hope the people who received financial support got some emails about boarding passes and whatnot, and about payments. But well, if not, please tell me. Maybe there was one speaker or poster presenter who didn't sign up for dinner. If you haven't, please tell me during the break. I was counting some heads and I was missing people. In any case, we can continue. It's a pleasure for me. I have my good friend and colleague from the Basque Center for Applied Mathematics, Luz Roncal, who will be talking about unique continuation properties.
Okay, so first of all, I would like to express my deep gratitude to Emmanuel and Mateus and Felipe, because this is an amazing opportunity to come to Rio. It's a wonderful city, and it's the kind of city in my case, I only knew from the pictures in the textbook when I was in the high school. And now it's impressive to see there all the nice things, so thank you very much for this great opportunity. So I'm going to speak about unique continuation properties from discrete to continuous, so probably this is more in the beyond part of Fourier analysis and beyond. But okay, so yeah, it will be about unique continuation. That is one of my the research lines I've been interested to in the last few years, and there will be some kind of lot of information because I try to present what I've been doing recently. Probably my idea is that if I could transmit certain ideas, especially for those people who don't know about this kind of research, then take them home. And of course, I would like to show you the precise topics I was interested and try to convince that there are nice results that somewhat they are also related to Fourier analysis. So let me start with a form of unique continuation. Okay, there are many forms of unique continuations of solutions to equations in general. So I started to say that if we have a second order analytic operator, second order differential operator, so we have a second order elliptic equation like this, PU equals 0. We say that this equation of this operator has a weak unique continuation property if the following happens. So we are in a domain, and if it happens that if the solution is 0 in any subdomain of omega, this implies that the solution is 0 in the whole domain. This means that the equation has the weak unique continuation property. Okay, so this is somewhat a way to express propagation of smallness. That is one keyword. And there are other forms, strong unique continuation that I didn't mention here. And what I want to say is that, well, there is a big story or history about research in this direction with even very well-known names there, even from the harmonic analysis part. And there are many examples when you consider, of course, just in the RD with the Euclidean Laplacian potential, and there are many results in this direction. I will not mention any of them. So actually, it will be interesting from my title that was clear. What happened when instead of putting here the Euclidean Laplacian, I mean the second order derivatives, you have some discrete operator, discrete Laplacian, for instance, here, okay? That means that the second order differences. So it happens that this kind of problem, to study this kind of properties, has been studied also in the literature. And there are several results and maybe also, names that can be familiar from the point of view of harmonic analysis or harmonic analysis and interaction with PDEs. And just to make some announcement is that what's happening is that this is not just, what's happening in this situation is not just a discretization of the continuum case. So actually these kind of properties are in general different when you restrict to a mesh or set D or a discrete setting, different than the ones that you have in the Euclidean case, okay? So, well, just also to announce a bit is like, I would like to show you how different are these results in one another setting. And actually my curiosity and my collaborators one was to try to understand what's happening if you try to approximate from the discrete to continuum, and even to sometimes to give some not known contribution in the discrete setting. Okay, so one manifestation, because unique continuation has a lot of concepts attached, and there are many ways to study this, and there are many quantitative and qualitative ways to study this. One canonical quantitative way to understand Greek unique continuation is via what is called three-ball inequality. So again, coming back to, say, complex analysis or more Fourier analytic part, a three-ball inequality is somewhat a manifestation of the so-called three-sphere Hadamard circle theorem, three-sphere Hadamard theorem, that in terms is very much related to three lines lemma in complex analysis. So, for instance, we say that a harmonic function in Rd satisfies three-ball inequality in this sense, okay? So we can control L2 norm of a harmonic function in a ball V1 in this sense, okay? So you have a control about what is going on in a ball a bit smaller and a bit bigger. So this is also called doubling property, and actually this is somewhat a convexity property of the solutions, okay? So what's happening if we turn to the discrete world? So we are in set D. Actually, we will take a mesh. So we will put an H here that is just a number greater than 0. So this is the discrete Laplacian. As I mentioned, this is a second order difference equation. So in such a way that when H tends to 0, we recover the second order derivatives, okay? So when we consider discrete harmonic functions, it turns out that this property, this three-ball inequality, is not true anymore. Okay, so this is well known. For instance, I would like to just refer some work by Gaudy and Malinikova, where they explicitly give some counterexample. And so if this is not working, a natural question is that, okay, so how much is this not working? Right? So then introduce, if we are in set D, introduce a scale H, and then try to see how this property deteriorates as long as H tends to 0. Okay? So in some sense, you should also be able to see how you recover the weak unique continuation property for the Euclidean Laplacian. So, okay, this is known, actually in the same work by Gaudy and Malinikova and parallelly Lipner-Mangubi. So they show that if you have a discrete harmonic function, then you have a three-ball inequality result with an error term, and when H tends to 0, this will disappear, okay? So this is a canonical result that, well, we would like to study in other contexts or try to get deeper into these things. And okay, so let's continue a bit. This is just a way to understand what is a three-ball inequality, by the way, or a convexity estimate. So I'm just drawing here a ball B1, ball B2, the red one, and the smaller one is the blue one. So a three-ball inequality is telling you that, okay, if you have a priori control of the mass, for instance, in the large ball, in the red one, right? So the red ball will correspond to this quantity. So if you have some control about that, then what this is saying is that, okay, you will be able to get some information on the ball, the intermediate one, the green one, in terms of the information from the small one, the blue one. Okay, so in some sense you are propagating what is going here towards the green ball. Okay, propagation of smallness. This kind of result is used to even to conclude unique continuation, in the sense that to conclude that U is equal 0 when you, for instance, consider even strong unique continuation like solutions of vanishing order, but I will not get into that. But this is something very basic, okay? So this is the idea. Okay, so the first question we'd like to understand is that, so this is happening for harmonic functions or discrete harmonic functions. Can one go beyond? So can one try to consider more general operators, even with potentials? And can one give some three-ball inequality result? Okay, so this is the first question we asked. And the interesting thing is the following. So if one looks at the original works by these people for discrete harmonic functions, the way to prove the failure of the three-ball inequality was somewhat mimicking the Euclidean one that is based on complex analysis. Because as I mentioned, this is essentially a meaningful interpretation of the three-sphere Hadamard theorem, right, for holomorphic functions. So the methods that these people used, in some sense, were following this complex analytic framework. These kind of proofs are very elegant, are very nice. We probably will not very classical, but sometimes they have some drawback. And one of the main drawbacks is that you cannot then introduce functional potential, or maybe you can introduce potential with very, very restrictive conditions if you want to apply this complex analytical framework. So, in general, in this kind of results, and this was a question that related to this even was raised for many people, including Terence Tao and so on. It would be nice to see if there is a real valued proof for this kind of W inequalities and so on, which could be more flexible in the sense that one could include other kind of operators. So, okay, I'm not saying more at this point about references, but I will say more later. So, yeah, so our first goal is to find an alternative proof to generalize discrete three-ball inequality to this kind of operators, okay? So, these are just keywords because I will not enter into many details and proofs and so on. So actually our approach is based, because, well, we are able to prove three-ball inequality. I will put it in some slides later. We are going to prove such a three-ball inequality by using specific techniques for the discrete Laplacian, using the fact that it has a specific form. And our approach will be based in the so-called Karleman estimates. Okay, that is another keyword that one could take home after this talk. So, well, it's a bit involved, of course, but the point is that at some point, by using this approach, one can reduce the proof also to some kind of pseudo-differential calculus philosophy, going to Fourier multipliers, and study low-high frequencies. This is more technical. And another thing that is important in this setting, and I will try to explain a bit more later, is that one needs approximation arguments to compare the discrete setting together with the continuum. Okay, so then our approach to prove a three-ball inequality for such a general operator that I mentioned before will be through Karleman estimates. Okay, Karleman estimates, they are weighted inequalities. Now this is general, okay? That in particular in this setting are very useful to prove kind of unique continuation results. This is present in inverse problems, control theory, not only pure PDEs. And, well, one has, this is a kind of form of Karleman estimate, okay? Remember that this P is our second order differential operator, or even other operator, like the general one that I put, so you can put potentials and magnetic fields and all this. So this will be controlling the L2 norm, well, I put L2, but can be other norms, of a weighted, this is a weighted inequality, and this phi is usually called a Karleman weight. So, of course, in this very general expression, there are a lot of information hidden, and this actually is a manifestation of, again, convexity properties of solutions to equations. So this weight here, appearing here, has to be somewhat related to the kind of convexity properties that your solution has. Okay, so the choice of phi In each situation, they will depend on the situation itself, okay? Another thing that is interesting is that this weight here, whenever you choose it, no, in a clever way, will be depending on a parameter. Okay, you introduce a parameter in this game, and then this parameter will allow you, after playing games, to deduce some quantitative estimates here and there, so that once you choose the precise parameter, you will be able to play a game of when the parameter is very big, then you will reach a contradiction, giving you unique continuation, okay? Okay, so this is I know this is very hand-waving, but at least just to crash course for that, it will be okay. So, which is the strategy to deduce Karleman estimates? So we are all the time staying in a real valued approach, just saying plain algebraic manipulations. So the point is the following. Usually the strategy is as follows. So you consider this operator, and then you split it into, I put here the discrete Laplacian, but this will be with the general operator you want to play with. But since I will present results for the discrete Laplacian, I put here discrete Laplacian. Okay, so the idea is to write this operator, this new operator, the conjugate operator, in its symmetric and antisymmetric part. Okay? So let's rename E to the phi u like V. Okay, and then you start in this situation. Okay, so you are here, so this is that. Spell out. Okay, so you have a square of symmetric, a square of antisymmetric, and the commutator. So, of course, this is positive, and then actually to prove such a kind of estimate, what you need to see is to ensure some positivity of this operator or some positivity of the commutator. Okay? So we need estimates of this estimate from below, so positivity. Okay, so these kind of ideas, maybe a reference, or basic reference is Agmon. Okay, was Agmon, Hormander. They were introducing these kind of ideas to prove unique continuation, and yeah, there has been many people working out these kind of things, and I would like to mention, although it will be mentioned later, so probably the team by Escauriaza, Koenig, Ponce, and Vega were able to exploit it in a very much abstract setting, just to give even some general paradigms, okay? Of course, these kind of ideas, as I mentioned, are very well known, especially among inverse problems control theory community. Okay, but this is the general approach to get a Karleman estimate, and this is a central concept to exploit in unique continuation. Okay, so I wrote here this, that because in our case, when dealing with discrete harmonic analysis, so in some sense, parts of the proof will be related to look at this commutator and try to get this positivity for this commutator. In the case of the discrete Laplacian, the computation of this commutator is a bit cumbersome, and then one has to look at the Fourier side and treat the terms you get like with some pseudo-differential calculus. Okay. Okay. So, well, so let's go and try to announce at least the result we have. As I mentioned, the key point in our study is to get a discrete Karleman estimate, which has this shape. Okay, this G is the discrete Laplacian on U, and actually you can put all other terms. So we are able to get this kind of inequality. Okay, so let's. There are a lot of information missing here because actually it was in purpose. So we are able to find a Karleman estimate. Here the weight has to be carefully chosen. Actually this follows some ideas by Ancana Ruland and Koch and Xi. The weight has some pseudo-convex properties that I will not get into detail. And the point is that this tau, that is the Karleman parameter that I mentioned, that will be important to choose to produce the unique continuation, or the three-ball inequality in this case, actually is allowed to be taken, and this is the important thing, in an interval which depends on the scale, okay? So actually, I don't remember how much I put here. I didn't put much. The point is that to produce this Karleman inequality, no, we do the game as I mentioned, get the commutator, expand it, and then what you obtain is a series of terms that are hyperbolic functions with arguments involving the Karleman parameter and the h. So then the idea is to linearize by using approximation arguments, and then once you linearize, you get Taylor. Then you have to constrain your tau and h to certain interval. So this is the responsible to getting some restriction on the mesh for the parameter tau. And this constraint, will be responsible to make some extra term arise in terms of h. Okay, so once, I will try to explain a bit. So once you have this discrete Karleman estimate, then you apply the Karleman estimate to a localized function. This is something very standard. And then you choose the weight conveniently. This is something that I mentioned. So with this idea, I'm playing this game here, you are able to deduce logarithmic convexity estimate like this, okay? So again, the tau is here, but tau is constrained to some interval depending on h. And again, now, an optimization argument for this, for the tau that I was appearing in the previous slide, leads you to such a three-ball inequality. So this is the three-ball inequality that we have, together with, this was together with the four people, Diana, Ankana, and Ingeru. So we essentially obtained the analogous result as Guadi, Marinnikova, Lipner, Mangubi, but for more general operators. Okay, here is arising the term, and as I mentioned, this comes from this optimization argument where your parameter is restrained because of these approximation arguments. Okay, so this is first result. Then let's go a bit further. Second chapter, say. The second problem we were interested was to look at, again, unique continuation properties, but now related to alpha or S harmonic functions. Okay, so let's come back to the Euclidean world, and then now let's consider the fractional Laplacian, or fractional powers of the Laplacian. Okay, so remember that, again, I will be interested in weak unique continuation properties. But now, in the Euclidean case, I will put, instead of P, I will put the fractional powers of the Laplacian. Okay. So what's happening in this case is that the fractional Laplacian satisfies something even more than weak unique continuation. It satisfies something called global weak unique continuation. This is also sometimes that, in the physical community, they call anti-locality, and this is what's happening. So this is a result in 2020 saying that, okay, let's take an open domain in RD, and let's take a function that is in HR for any R, and let's assume that we have that this function is S harmonic in omega, and also the solution vanishes in omega. So it turns out that actually this propagates to the whole Euclidean space. Okay, so if you remember when I presented, here it is, when I presented weak unique continuation, we are all the time constrained to a domain, but here what you do is to propagate from a domain to the whole RD. So this is called global unique continuation. This property actually was not new. This was known from all results by Marcel Ries and even in probability setting. Here the novelty by these people is that you can assume U to be the solution of this equation, but in HR, okay? Okay, they were motivated by some inverse problem, and in somewhat is surprising, no? It's, it's a property that the fractional Laplacian has. So now the question is again, so if now I put here a discrete Laplacian, and I consider the fractional discrete Laplacian, which is the global unique continuation. Okay, so what's happening here is that again, this property fails in the discrete world. So, well, this was the question now. Study discrete counterpart of global unique continuation for the fractional Laplacian on H set D. And actually what's happening is that this property fails in this setting. No? So actually one can give me a finite set of cardinality n in the mesh. So you can find a non-trivial sequence on the space of function for which the discrete fractional Laplacian is defined, such that is S harmonic and the solution is 0 in this setting. Actually, the way to prove this is not very difficult. You have to play with the idea that the discrete harmonic analysis has a very precise form with a symmetric kernel, and there is a counting measure, and it's a matter of playing a bit with the symmetries of this kernel in this setting. And then the question is that, okay, now again, this property is failing. How much is it failing? Can one give some result a la Wadi Malenikova saying, okay, this is going to fail like that? So this was the question. Before that, I would like also to mention that there are forms of global unique continuation for the discrete fractional Laplacian that still persist. For instance, something like what is called global UCP from the exterior. So for instance, if you have an S discrete harmonic function outside a ball, right? So something that you have but something that is 0 outside. So this will propagate to the whole mesh. Okay. So oops. Here. So this still persists. Actually, I would like to present a short proof of this fact that actually this is not also very original, but I like because it has to do with analyticity and Paley-Wiener and maybe Fourier and beyond. So okay, this is going to happen. Proof. The proof is based on Paley-Wiener theorem and branch-cut property of the analytic extension of the symbol. So, contradiction, it will be by contradiction. So assume that the U will not be 0, okay? So that means that we have compact support. Then the Fourier transform of these functions will be analytic and non-trivial, okay? Then you have an analytic extension, okay, to the whole strip in CD. So what's happening here? Okay, so look at the symbol. So the symbol of this operator is something like sines to the power S. So you have the Fourier transform, discrete Fourier transform of U that is analytic. So this guy is an analytic function of G because this is an analytic function. So now, pass this thing, so actually I said all this is analytic, so this is a function that is analytic. Okay, pass this dividing here. So this is meromorphic, but then this symbol has a branch cut. This is not meromorphic. So contradiction, okay? So this is very, very nice proof just to see that this kind of unique continuation still persists. Okay, so good. Then the question is that let's come back to the general situation. In general, you don't have a global unique continuation for the discrete harmonic fractional discrete Laplacian. How can one measure the failure of this property? Okay, so this is one way we found like to show it. Okay, let's come back to the Euclidean world again. Okay, so another way to prove unique continuation in the Euclidean case, or another form of unique continuation in the Euclidean case, is through the harmonic extension. Okay? So let's look at the solutions of this function. Of this equation. This is in the upper half extended plane, so RD plus 1. When S equals 1/2, this is just the harmonic extension. Okay? Good. So there is a work by Jerison and Levaux saying that, okay, if you give me a weak solution of this equation, no, in the upper half space, then you can deduce some kind of three-ball inequality. Now here you are mixing U, that is the solution in the extended upper half plane, and with the boundary term. Okay, so this is a kind of three-ball inequality in this setting. So actually from this inequality, from this three-ball inequality for harmonic extension, you can deduce from here unique continuation, weak unique continuation, global unique continuation, and even strong that I didn't define. Okay, so there is another way to get the unique continuation. So, what's happening? In the discrete case, we prove that the global unique continuation is not possible. So, such a kind of result cannot be true in the discrete case, right? Putting here a discrete Laplacian and extend it, then this result has to fail, because otherwise we will get the global unique continuation that is not true, right? So, okay, so how much is gonna fail this? Since we have experience, because we were dealing with three-ball inequalities, we can again try to produce a three-ball inequality in the upper half space with a discrete Laplacian to see how much the failure is coming. Okay, so this is the strategy, and this is actually, well, this is just what I just explained. So in our case, this fails, this cannot hold, no, because of the result that I mentioned. So how much this does not hold? So let's try to look at such a kind of three-ball inequality and see where the result fails, right? So actually this is what we did, and this is how this quantitative boundary bulk, let's say, unique continuation fails when you put here the discrete Laplacian. So actually again we can obtain a three-ball inequality plus the error term. So again, if H is going to 0, then will disappear and you will recover the Euclidean result. Okay, so, oops. Yeah, well, this probably is totally irrelevant because I didn't enter into details, no, but so the proof is not totally analogous as in the previous situation. Actually, it's slightly simpler because of the geometry of the problem. I will not get into details, but at least we learned from the previous situation that well, we could try to get such a three-ball inequality. Okay, so then in the time that is missing, that is 20 or 20. Then I will go to a second part that is another kind of unique continuation. Okay, and this is something that a problem that well I like very much. I think is kind of very nice. So okay, now I'm going to talk about so changing gears. We are going to talk about unique continuation at infinity. Okay. So this is probably the seminal question in this problem, is that, okay, let's consider a stationary Schrödinger equation with an RD, and there is a conjecture by Kondratiev and Landis saying that, okay, if the potential is bounded and U, the solution, decays bit super exponentially, then U will be 0. Okay, and suppose that this is sharp. This is the conjecture. Okay, so in what follows, what I will call a Landis type result, a bit maybe forcing a bit the concept, is that I will be interested in the maximal vanishing rate of solutions to equations with potentials. That means that, okay, I will call Landis type results. If I instead putting here delta, I will put a Schrödinger equation, a non-stationary Schrödinger equation, or even parabolic or whatever. And then I will impose time decaying condition to see if I can deduce U equals 0, and which are the maximal vanishing rate of decay of this solution. Okay, this will be the question. Okay. So some story about the original problem. So this conjecture was disproved by Meskov in the 90s. And actually he managed to construct a complex valued potential, a non-trivial solution, such that decay like this. And actually this is sharp, in the sense that if you decay a bit more than 4/3, then the solution is 0. Okay, so in words, the exponent 4/3 is optimal when you consider a complex value potential. Question, what happened if, well, before that, this is also a very important point to recall. There is a quantitative form of Meskov result, in the sense that giving some lower bounds of how small can be the solution, present in a very nice paper by Burgan and Kenny in 2005. This work is related actually to some other problem that's also very interesting in the physics community, that is, or the mathematical physics, that is relates to the study of eigenfunctions for the so-called Anderson-Bernoulli model, which is a model in which V is a potential taking random value 0, 1. Again, I will not enter into details, but the point is that, so there was a part of this problem, well, this problem actually is open in higher dimensions, higher than 3. But at that point, there was a point in which the problem was stuck when considering certain potentials, and the idea was to introduce a Karleman method in part of the proof that produced a quantitative unique continuation. Okay? So this allowed them to prove what they wanted, and also they introduced a way to look at quantitative forms of unique continuation for this problem. Okay, so this is a very important paper. So after that, as I mentioned, Koenig asked what about real valued potentials if you can get a Landis conjecture. And I put two, I think, important results. Koenig-Silvestre 1, they proved that the conjecture is true for dimension 2 and non-negative potential. Actually, in this situation, the problem is trivial. The point is that they put a divergence first order derivatives here, and also they give quantitative form of unique continuation. And probably this is maybe the most remarkable result so far. So Logunov, Malynikova, Nadir-Ashvili, Nazarov proved the conjecture to be true in dimension 2 and for real potential, not only non-negative. Okay? There are other recent contributions by Filonov, Krinsky, and Logunov collaborators, but probably I would like to leave this as a remarkable result. And then beyond that, the D greater than 3, this is open. Okay. Okay, so as I mentioned, for me, I will call Landis type results those in which you can only not only consider the discrete the Laplacian here, but probably other kind of equation, parabolic dispersive, but with potential. So, for instance, in this case, these people, Escariaza, Kenny, Poncevega, that I mentioned before, they, in a series of papers, they managed to prove that under conditions on the potential, if U is a solution to this equation with satisfying 2 time decay conditions, and here there are 2 parameters, alpha and beta, such that this alpha beta satisfies this, then U equals 0, and this is sharp. The same kind of result for heat equation, okay, so we have the solution of a heat equation with potentials satisfying something, and we have in 1 time decay condition with a parameter such that something is happening, then U equals 0. One word here, I mean, probably will not reach the end, but at least will be pedagogical. So, again, here, because this has much to do with Fourier. One of the important and very interesting things with these results is that they are interpretations of the Fourier uncertainty principle. Okay, that function and Fourier transform cannot decay simultaneously, and then there's a condition on these parameters, so that tells you when this is happening and when it's not. So there is an equivalence of this result and this result here with potential V equals 0. Okay? So there is an interpretation of Fourier uncertainty principle in terms of solution of Schrödinger equation. And also the point is that these people, as I mentioned, introduce a real valued proof based on these Karlemann inequalities and so on, so that they allowed to introduce more general potentials here, introduce potentials itself and more general conditions. Okay, so this is a nice series of results and somewhat inspiring. So then the question will be to make these questions about Landis type results, but for discrete setting. Okay, so this is our interest. So for instance, if we look at the non-stationary discrete Schrödinger equation, put here the discrete Laplacian. Okay? And we will put a potential that is bounded. So what is done in this direction? So there is a result by these two teams of people, giving a kind of Landis type result or dynamical uncertainty principle is called actually generally. So they say that if you have decay, two-time decaying for all points in set D of this form, then U has to be 0. And this is essentially sharp. Okay? So let's look at the following. So here the decay they are asking is of the form n log n. In the results, in the continuous setting, you have Gaussian decay, because also this has to do with the Fourier uncertainty principle. So then this is a big gap, right? N log n or square. And well, this is one of the motivations to see what is going on in between. No, that's this. I am giving a hint of what did we ask ourselves. So just to mention the way to produce the result that this team used. I mean, Jamin, Liwaski, Marikov, and Perfect again, they proved such a kind of thing by using complex analysis. They consider potentials, but with very restricted conditions, and then Anguero and Luis Vega, they use the real valued approach based on Karlemann estimates. And actually, in this situation, one has to work a bit hard, because in some sense, they have to produce an upper bound and a lower bound, and then confront a certain parameter that is happening, as I mentioned, to produce a contradiction. So in this situation, essentially, this is what I'm saying, no? One has to produce an upper bound, and this is based in, again, convexity estimates, okay? You have to produce a lower bound. This is based in Karlemann estimates, based on commutators between symmetric and antisymmetric. Okay, so this is the approach by these people, and then we ask the question that, okay, introduce a scale, h, in this context, and can you see how are you interpolating between discrete and continuous? So that was our question, and yeah, okay, so I don't know, I have to cut, but I don't know where. So this is the question. We started to look at the problem, but not for the Schrödinger equation, the non-stationary, but for the heat equation, because it's like a test. Okay, it's slightly easier to deal with, and also because these kind of techniques that I mentioned of the commutator, Karlemann estimates, if you look at this kind of tools here, then to deal with the stationary Schrödinger equation is somewhat a byproduct. Okay, so well, we decided to look at this and then try to study what's happening with Landis type result for this, and also see what we have for the stationary Schrödinger. Okay, so then we obtain, and probably I will have time to present the results and not very much. We got some qualitative estimates, so under assumption of two-time spatial decaying conditions on the solution, we were able to say that the solution is 0, okay, Landis type. And the way to get these estimates will be through quantitative estimates, upper bound, lower bound, what I said, but in two regimes. In a regime that is close to continuum when the h is closing to 0, and in a purely discrete region, in the sense that give me any h, we are in a pure discrete scale grid, and we got which kind of two-time decaying condition we have to deduce the uniqueness. So, okay. So this is the result we got for the regime that is close to continuous. So let's consider the heat equation, no, with a discrete Laplacian, and let's assume this two-time decaying condition. So here omega is this ugly object involving, well, this is a normalization thing, k naught, but this k, jk are McDonald Bessel functions. So this is very weird in principle. So what we are saying that, okay, essentially this is dictating the decay. So if my solutions in 2 times decay like that, and this is an L2, little L2 in space, then there will be a threshold and certain parameter such that if I am arbitrarily small, then you will be 0. Okay, so which is the motivation for this decay condition? The motivation is actually because you can see this function as a discrete version of the decay of the inverse continuous Gaussian function. Let me explain. So, in the continuous case, you have that the decay conditions are determined by Gaussians, okay? So Gaussians are essentially fundamental solution of the heat equation. So it is known that for the semi-discrete heat equation, the fundamental solution is actually given in terms of this I Bessel function, the modified Bessel functions, whose behavior is like that. Like, remember, nu here is the space, because it's J. So the fundamental solution to the semi-discrete heat equation is something like this, behaves like that. So the inverse is precisely these functions. So it was reasonable to look at this decay condition, because this was the inverse of that. And actually the things went through and actually matched what one was expecting. Okay, so let me now be a bit fast, because actually, the parameter plays a role, like delta, in this heat dynamic uncertainty principle in RD. I will go a bit fast, because, I will not explain this, because actually there is a meaningful interpretation of convexity behind these results that essentially you have to look at, again, convexity estimates or doubling condition or kind of three-ball inequalities, but in a dynamical situation. And actually this has to do with the computation of the commutator. Of course, I will not go through this because I don't have time. But I would like to just to show you the two quantitative upper and lower bounds. So as I mentioned, to get this result that I just showed, one needs to get two estimates, quantify them in some sense, and then get a contradiction. So one is first an upper bound. This is the upper bound. So under the same conditions that I mentioned, you can find a threshold for that, such that if you fix restricted mass L2 estimate in a restricted annually, okay? Here you are quantifying by this capital R. Then one gets that this quantity is smaller than the exponential minus d R square gamma. Okay, here is coming the Gaussian in some sense. So as long as you are approximating to 0, then you get an upper bound that for the L2 norm of the solution in a restricted region, which is like a Gaussian, okay? And then the lower bound that I have, to prove this thing, you need these convexity properties that I didn't mention. And here is when you are looking at, when you are seeing essentially the two regimes. So the second quantitative bound you need is a lower bound for the same quantity. So the result we obtain is the following. So you can find a threshold so that if h is arbitrarily small, the lower bound here is given by the Gaussian. in a certain regime that is close to the continuum case, in the sense that H is such a small, so that this RH, R is an analyte that you are fixing, this is very small. So if you are in a region, so this has to be understood, like if you are in a region of given H, so that this is collapsing to the continuum case, then you have a lower bound for this quantity that is like a Gaussian. If you are in a regime in which you are essentially fixing a scale H, so that this is big, right? So then you are getting a lower bound that is essentially the bound you have for the discrete Landis type unique continuation of Malinnikov and the others, or Aingeru, Fernandez, and Luis Vega. Okay, so here is the gap, and here is where the two regimes are arising. Actually, the proof of this is a consequence of a Karleman inequality, and at some point, again, you have to remember the key ideas. To produce this, you have to look at certain symmetric, antisymmetric commutator. You have to look at the positivity of the commutator. As I mentioned, you had here hyperbolic functions with arguments involving H and, well, all parameters. When you linearize, at some point you have to look at these hyperbolic functions. So if you linearize, then you have to look at regions which are small enough, or you can look at asymptotics for these hyperbolic functions which are big. So this dichotomy is giving you then you have to look at certain regions that are like this, or certain regions that are like that. So certain regions that are collapsing to the continuum, this is giving you the Gaussian. Certain regions that are keeping in a discrete scale, this is giving you like a scaled version of Fernandez, Bertolin, Vega, or Jaman, etc. Okay? So, well, I will not go into details, but I hope at least you understood something. Okay, just 1 second. As I mentioned, yeah, because that's because I think it's interesting. As I mentioned, with the study for the heat discrete, as a byproduct, you could deduce results for the stationary Schrödinger equation. This is like the genuine discrete counterpart of Landis conjecture, okay? So it happens that we have a result saying that essentially, when you are in a fixed scale, if you ask for a decay that is J log J, then you can conclude that U equals 0. But if you are approaching to the continuum, then the decay you assume is minus 4/3. So if you assume minus 4/3, then you can deduce that U equals 0. So this is matching with Burgan-Koenig or Meshkov, right? We don't know if this is sharp, and actually we think that it's not, because I didn't mention, but yeah, all the proofs going through Karleman inequalities don't see the complex or real value nature of the potential, but the approach by Logunov, Malinnikova, etc., in their last breakthrough goes through complex analysis, quantum-conformal mappings. I don't know if we don't know how to modify the proof just to try to see if one can reach L log L, or L log L 1/2 actually that they have. But anyway, this is everything. I hope you learned something. Thank you.